Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Design News webinar, Getting Started with Integrated Actuators in EtherCAT, sponsored by Harmonic Drive and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. This webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speaker, download resources, share this webinar, and participate in the Q&A session that takes place at the end of our presentation. Toward the end of our webinar, we will ask you to complete our survey. Please take a minute to fill out this webinar survey before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. The slides will advance automatically throughout the event, and lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen, or type your issue into the Q&A area, and we will be glad to offer one-on-one assistance. Now on to the presentation, getting started with Integrated Actuators in EtherCAT. Discussing today's topic is Marcel Almonte, Mechatronics Applications Engineer at Harmonic Drive. To learn more about our speaker, please visit the speakers widget. Marcel, over to you.
Hello everyone, my name is Marcel Almonte. I am a Mechatronics Applications Engineer working for Harmonic Drive, and today I'm going to teach you how to get started with integrated actuators in EtherCAT. So let's begin with the agenda. So we're going to cover integrated actuators, trends, benefits in our lineup, getting started with EtherCAT, and we're going to step into EtherCAT communications, and I'm going to show you a few demos along the way. So some of the trends in the robotic industry that we've seen here at Harmonic Drive is more compact designs, localized control, and an increase in power and torque density. So with this being said, the way we've essentially addressed these trends are by going for similar form factors, by supporting a large range of ratios in a similar package, LEMO connectors for plug and play, which allow you to, instead of having to run multiple cables out through a flying lead, essentially it's just a push pin, pop it right in there, you're set to go. And the integration of hollow shafts to let you run cables through these. And so the whole idea is when you simplify cabling and you simplify actuator design and you pair a motor and a driver together, it allows the end user much more freedom in their design in terms of, oh, I have more space to work with, I have more potential to create a great product. So now that I've discussed the trends in the robotics industry, I wanted to touch upon the benefits of integrated actuators. So when you have an integrated actuator, you have a BLDC driver right at the source of motion. So you reduced any of the propagation delays in your cabling, you simplified the cabling out of the integrated actuator by either having power or communications, or power and communications for can open variants. And instead of having to buy an external driver, you can essentially just buy the whole package inside of the actuator, which really allows you to save space in your cabinet. So here are some specifications for our SHA series and our LPA series actuators. One thing I want to mention is the very high maximum torque that you may see for the SHA series. And one of the things that makes this actuator really special and what it's really good at is holding that stiffness, holding that repeatability due to the zero backlash design in the strain wave gear that's inside of it, and allowing you to run it on a lower bus voltage, anywhere from 24 to 60 volts. So this is great for any mobile applications or applications where cabling is a constraint and you need that extra power to really lift some heavy stuff. The LPA also offers very good maximum torque with the peak value of 57 Newton meters for the 1:1 ratio. And both of the SHA and the LPA have dual absolute encoders. So this allows you to really have confidence in your positioning. So here we can see a layout of what our actuators support. The ones on the bottom, the ones we're going to be talking about today, the LPA and the SHA, but we do have the RSF5 and RSA8 as well as the FHA series. So all of these actuators can be geared towards lower voltage as well as higher voltage depending on your application. And they support CAN open and EtherCAT communications. All of these integrated actuators do have options for I/O if you need to drive a sensor. And this allows us to have extra level of safety if we wanted to integrate some element of motor torque off. If you're looking for more information on our integrated actuators or information on potential applications, You can find more on our website, harmonicdrive.net, and on our YouTube page, Harmonic Drive LLC. Get started with EtherCAT. So EtherCAT is for control automation technology. That's essentially what it is. It's Ethernet for control automation technology. And what's happening here is it's using Ethernet-based systems for industrial automation. And this specific protocol is geared towards efficient communication between devices and making sure you have real-time principles as well. So EtherCAT sticks in a few different layers of the OSI model, specifically the physical, data link, and application layer. And it uses standard Ethernet network topology, which allows you to do different types of network configurations, such as line, ring, or star. The whole idea of using EtherCAT for this real time is you have this principle called essentially processing on the fly. And so what this does is, as you have EtherCAT communications going on, there essentially is, I kind of like think of it as a dinner plate. And on this dinner plate, what happens is I have a certain menu, and on that menu I have 3 nodes. Those are my 3 customers. Those are also what can be considered as our sub-devices. And as this EtherCAT plate passes through our network, what happens is those specific customers look at this plate, they put the stamp saying, yes, I viewed it, and then they say, oh, this information pertains to me. I'm going to add my part to this and then take off what is relevant to me. Then I'm going to pass it on to the guy to my side. So EtherCAT realizes there's a port open to its side. It passes the plate along. The next node gets it. They stamp it as well. And they say, okay, the information from the node previously doesn't particularly pertain to me, but this specific information does. I'm going to add my component to it. And then as these iterations pass through the node, what happens is the working counter iterates, saying, okay, I viewed this successfully, or I was able to read and write this successfully. But say, for example, as this plate goes to the next person, and they drop the plate. They say, oh no, I dropped the plate. What that is basically a simile for is losing or having a broken connection. And so what happens is, oh, looks like they dropped the plate. What we're going to do is we're going to send up our plate to the person who's before us, and then go back up to our main device. So the whole idea, in a general sense, is you have distributed clocks throughout the system, which allows you to have very, very precise timing with nodes that can be particularly far away from each other. It allows you to pack in protocol-specific information that may pertain to different devices. So I kind of view this as, maybe this customer has a certain appetite and they're a sensor. And then this customer has a certain appetite and maybe they're an actuator. And the whole idea is that whatever is particular to them can be added to that frame in real time and then passed along to the next essentially customer in that chain. So the whole idea with this is you have a very, very large, robust network that has distributed clocks. It processes the frames on the fly. And if there's any break in the network, it can understand this and send the frame back up the way it came. And the whole idea with the whole synchronization component of it is you can either base your clocks off of your computer, you can base them off of the sync manager, or you can base them off of distributed clocks. So I'm going to go into more detail about this after we do our initial setup demo, but I wanted to just lay that out now. Okay, so this is our EtherCAT main device. And what's happening here is your main device, which is your embedded PC in this case, has an ENI file. This is basically your network initialization file. And what happens is, in this ENI file, there's an EtherCAT configuration tool that recognizes, hey, on your network, you have these actuators. And based on these actuators, what's going to happen is it's going to look for that ESI file, which is your EtherCAT subdevice information file, and it's going to use that to configure your subdevices on your network. So when your network initializes and then goes into your, essentially, your pre-operational state, the master is basically looking for these ENI and ESI files. So when it realizes that, it says, oh, look, there is an LPA 20, and you are this type of device. I will configure you as such. And this is what happens when the network is initially started. So this is our EtherCAT subdevice. And so I wanted to draw your attention to 3 different layers that you can see. So at the top, we have the application layer. In the middle, we have the data link layer. And at the bottom, we have the physical layer. And the whole idea is this is kind of what summarizes what's inside of your EtherCAT subdevice file. The top layer is the different types of communication protocols. The data link layer shows what's happening inside your sub-device controller. Specifically, you have things such as mailboxes, you have sync managers, and you have field bus memory management units. And what's happening here is these elements are used to store information about your sub-device, as well as monitor communications and configure data objects for that sub-device. On the bottom, we have our physical layer. This physical layer has our auto forwarder and loopback. This is what I was mentioning before, where the EtherCAT system looks and says, hey, is there something connected to you? If there's not, I'm going to pass the frame back up the way it came. So that's what we can see at the bottom right here. And the important thing to note is that in our sub-device information, we have specific information about our vendor ID, product code, serial number, as well as general communication parameters for our sync managers. So what we have here is a picture of our EtherCAT LPA20 variant, and on this specific diagram we can see our power, our I/O, our EtherCAT in, and our EtherCAT out. So in a general sense, you can see what is going on in the background of the microcontroller. So you have the microcontroller that's connected to your EEPROM, you have it connected to your EtherCAT sub-device controller, and you have it talking to our various encoders and BLDC drivers inside of our actuator. So one of the things I want to draw your attention towards is the I/O. The whole idea behind this is you can essentially drive other I/O devices from this I/O port. So say, for example, if you had a sensor or a touch probe or something of that nature, there is a capability to connect that to the I/O port. Now that I've covered the basics of the types of devices you may encounter in an EtherCAT system, I wanted to briefly touch upon the modular device profile. The reason why I wanted to touch upon this is something that's specific to EtherCAT. The whole idea behind the modular device profile is you have two types of devices. You have logical devices and you have physical devices. An example of a physical device would be a gateway, for example, a can open gateway, or some other flavor of communication gateway, versus an example of a logical device would be something such as a DS402 can open actuator. And the whole idea is the modular device profile is used to map out different types of data object inside the main device, as well as know roughly what type of sub-device is connecting to it, and helps you pull in other information about that sub-device to connect to objects inside of the main device. So when your system initially starts up, what happens is your main device recognizes your sub-devices and says, oh, since you are this type of device, I'm going to configure you as such. So this can help with the setup process and make it much easier to get started if you're aware of this, versus going through and manually mapping out all of the objects to the main device. Last thing I wanted to touch on was EtherCAT state machine. I'm going to go in more depth into this in the future of this presentation, but I wanted to briefly touch upon this so when I show you guys the setup video, it makes a little more sense. So what we have right here is our EtherCAT state machine. You're going to see a few different types of states. You're going to see init, pre-op, safe-op, operational, and bootstrap. The main thing I wanted to draw your attention towards is this table on the right. So the whole idea is when you first start up your device, it's going to be in the init state. And then once it says, hey, everything is good, it's going to then automatically transfer to your pre-operational state. This is where it's going to enable mailbox communication and initialize any distributed clocks if you have them enabled. And then once this is all set, it's going to say, hey, my sub-devices are okay, I'm going to go into safe operational stage. In this safe operational stage, what you're going to do is you're going to configure your process data objects. These are your cyclic data communication, stuff that is related to your actuator, such as, hey, what is my current position? Or, hey, what's my current status? Stuff of that nature that is being cyclically pulled. And then once your system is in the finally stable state, it'll transition to operational. This is going to turn on the output data from our network. Okay, I'm going to walk you guys through the setup of an EtherCAT, TwinCAT system. So the first thing I'm going to show you guys is the system diagram. Then I'm going to go over what you need to know for the initial setup, and then we're going to go over a live demo. So in our specific EtherCAT setup, we have an LPA20, we have a DC power supply, we have a CX5 330 embedded PC, an EL6751 CAN Open Gateway, and we have an EK 1100 EtherCAT terminal. So in this specific setup, we have an Ethernet cable that's plugged from our PC to our embedded PC. And we also have an EtherCAT cable going from our EK 1100 to our EtherCAT import of our LPA20. So before we do this, we have to do a few separate things. First, we got to make sure that we have XAE TwinCAT 3 on our PC. You can definitely find more information about this on the Beckhoff website. They have a great series of trainings related to getting started with TwinCAT. And I would also point you guys towards making sure that you guys have the correct ESI files inside of your TwinCAT 3 folders. This will allow, when you connect your sub-devices, to properly recognize them and say, oh, I know what you are. These are all your parameters. You have the option to read parameters from the device when it's online, but it's not going to have the full comprehensive list. Just enough to get you going, but there's certain objects you may want to have full descriptions for. The other thing you're going to do is you're going to make sure that your main device and your PC have the same subnet, and they must be unique. For example, you can have 192.168.1 and then whatever you choose for your main device, and then you can have something similar for your PC. And this will allow you to properly recognize the device. And then once you start up your system, it's going to ask you for trial licenses if you haven't already purchased licenses for your modules. So that's just something else to consider. So now that we've discussed the initial setup, what I'm going to walk you guys through is essentially how to make some motion. All right, let's talk about creating motion with numerical control. So numerical control, or commonly referred to as NC, uses the automated control of machining tools by a computer and involves pre-programmed commands. Stuff like, hey, jog the actuator, jog the axis, reset its position, home. I like to think of this as the bare bones of creating a motion control project. So what happens is when you use NC, it essentially exists in what's called the soft motion layer. This is a layer that sits between your PLC and your field bus. And the whole idea is it helps translate some of those commands from, say, a user interface, such as like jog, to actual specific commands in your system. So what this is great for is for point-to-point motion, as well as general troubleshooting when you're initially are creating a system. So I'm going to be using this specific numerical control functionality to create motion with our actuators.
All right, let's create a new project. Once you've created a new project, in order to connect to the main device, the IP address of your PC and the main device must be unique and on the same subnet. Since I've already configured these settings in the past, we are now going to scan our network for our main device. Now that I've scanned the network, I'm going to click Add Route. We're going to uncheck Secure ADS, and then we're going to use our default password, which is 1. Now that we have added this device, we can now select it as our target. Now we are going to open up the I/O drop-down. We are now going to click Devices, then right-click, then click Scan. We are now going to click Device 1 for EtherCAT, and then click Yes when it asks to scan for boxes. We are going to click No on the CAN Open Master, and click NC, and then OK. We are then going to click Yes to enable free run. This screen here shows us our object dictionary for our main device. In the Online tab, we can see which devices are connected to our main device. In this case, we can see the LPA20 is connected, and it is also missing an EtherCAT link, which is noted by the open connection on the port. Here we can also find objects related to our main device's state machine. If you click Drive 5, then click the COE Online tab, we can see actuator-specific objects. In this screen, we are going to change two objects. We are going to change our velocity window settings and our position window settings. Making these larger will make the initial troubleshooting much easier, as we will be much less likely to trigger a following error. For our final application, we will make these smaller depending on the performance we want. The next two objects we have are the control word, which is used to change the state as well as enable motion in the sub-device, and the status word, which indicates our current state and status. Another important object is the mode of operation and mode of operation display. This will change depending on the type of mode you're in, such as cyclic synchronous position or cyclic synchronous torque, for example. In the Online tab, we can see the current state of our actuator, which is indicating we are in operation mode. This is our Startup tab, and here we can configure the default mappings of our PDOs during the startup sequence. Now I'm going to draw your attention towards the motion section, where we are going to find axis 1. Here we can find our axis type and also change our units. In this case, we're going to change them to degrees. Now that we have changed our units, we can verify this change in the Parameter tab. Here we can also change our error propagation mode. I am now going to draw your attention to the encoder section, which can be found under axis 1. Since we have a 15-bit encoder and one rotation is 360 degrees, we're going to divide 360 degrees by 32,768, and then we're going to divide it by our gear ratio. This will give us our numerator scaling value. One thing to note, this is using the COE object 6064, which is the actual position value stored inside the actuator from the motor side. In the Drive tab, we can also find our scaling settings for position, velocity, and torque. We're also going to set our following error calculation to external. This will allow our following error calculation to be handled by our actuator instead of TwinCAT. In our control section, we can find our values for tuning as well as the type of controller we're using. These tuning values are used with the main device, and there's a separate set of tuning values stored on the sub-device. Now that we have set our initial parameters, we are now going to activate our configuration. This will place our system into run mode. Now we're going to click Drive 5, and we'll notice we have two new tabs. These tabs are NC Online and NC Functions. Before we can jog our actuator, we need to enable it. So we are going to click here, then click Controller, and then enable Feed Forward and Backward, and set our override to 100%. Now by using the F2 and F3 buttons, we can jog our actuator clockwise and counterclockwise. We can find additional supported modes in the NC Functions tab. In this case, I'm going to show you how to make an absolute move. So with absolute moves, this is a good way to check if your scaling is correct. For example, I'm going to make a 360-degree move, and this will end up in the same position that I started in. We're now going to use the sinus oscillation mode. This will be helpful in tuning the system, as well as allow us to make a sinusoidal move. Next, I'm going to show you how to add a scope to your project. This will allow us to monitor our position, velocity, and torque, which can also be helpful to understanding how our tuning is influenced. We're going to select the actual and the set values for each of these. I like to use the YT plot to show these values over time. We can now press the record button in the top right corner to start recording. The colors at the bottom left will tell us which values indicate what. This way we can compare, for example, our set velocity and our actual velocity. We are also able to change the frequency of our oscillation, which is inside our NC functions tab. One thing I want to mention is that there are two sets of tuning parameters. There are tuning parameters found on the actuator, and there are tuning parameters found with the main device. So when you're tuning the system, be aware that there are two places you can find this information, and they are separate.
Okay, now that I've shown you guys how to set up a system using an LPA, I'm going to step more into the communications with EtherCAT. This type of information will be helpful when troubleshooting the EtherCAT system, so I figured it'd be good to touch upon these topics for reference. So the first thing I'm going to talk to you guys about is the common protocols that we are using. So we are using FOE, file access over EtherCAT. This is specific to firmware updates. So either there's a new update that's released for your actuator, or you need to roll back to a different version of firmware that is specific to you, or something of that nature. The next one we have is COE. This is can open over EtherCAT. So the whole idea is this supports process data objects and service data objects. And more information about this can be found in the ETG 1001. And I just wanted to highlight upon which layer this takes place in. This takes place in the application layer, and specifically related to your main device. So inside of that, I wanted to talk about EtherCAT frames. So EtherCAT frames have a few important components. First of all, there's an Ethernet header, which has the MAC address, source, general Ethernet information. And then inside of that, we have an EtherCAT header. This has EtherCAT specific information, such as the length of data and the command type. And then inside of that, we have a data selection. This is where the payload would typically exist. And what I'm going to show you guys coming up is the different types of datagrams you may encounter. And then another important element of this is the working counter. So every time an actuator or a device on the node has successfully read the frame or written to the frame, it iterates the working counter. So this is kind of similar to like having a checksum when your system is communicating to make sure that that information has been passed through. And the last one we have is an Ethernet CRC, cyclic redundancy check. This makes sure there's no errors inside of the frame. And one other important portion that's specific to EtherCAT is sync managers. And these essentially monitor mailboxes and process data in your network. So in this diagram here, I wanted to draw your attention towards how frame processing actually works in the EtherCAT network. So the whole idea is when you have a device connected on an EtherCAT network, you have an EtherCAT in port going in, and then you have an EtherCAT out. If there's nothing connected to this EtherCAT out port, it'll then pass that on to the same direction it basically came up. But if there is a device that is connected, it'll allow you to pass that frame to the other device. And once it essentially goes to that ring, line, or whatever it's connected to, it'll then come back to this node and then pass it up the chain again. So the whole idea behind this is it allows you to have very different types of network topologies and build them off of each other, which is great when you're building industrial systems because you don't necessarily have to worry too much about how you're going to lay out the cable, especially if it's already been laid out. So this is inside of an EtherCAT frame. So inside of an EtherCAT frame, we have our header, and this is an example of what data you may encounter, as well as our length. So in this case, it says, okay, you have 24 bytes, which is indicated by the 0018 hex value. And then on the right side over here, I want to draw your attention towards the different types of commands you may encounter. So in this case, we have a logical read-write, and I'm going to go into depth more about the types of datagrams and where these commands are used. But this helps you roughly understand what's going on in the network. So if you had an issue with your network or you're trying to troubleshoot what was going on, this can help you briefly understand what process was going on in the background when this had occurred and what type of data was it using and where was it trying to go. So I typically would capture this using a tool like Wireshark and then analyze and compare this to the various types of commands here and see what that node was doing at that time to have a rough idea what was going on. And so, as I mentioned before, there are a few different types of EtherCAT datagrams. We have our state datagram example 1, which is I consider to be application layer state changes. We have another datagram, which is mailbox communication, and inside of that, I guess, main bucket, we have COE, can open over EtherCAT, service data object communications. And so an example of this is, say this is acyclic data. I want to read the maximum current off of an actuator on my network. So in this case, it would make sense to use a service data object because it's not a cyclic type of communication. It's something that I just need to check on this one parameter infrequently or however often I please. It's not something I want to be continuously polling. Versus the last example we have is process data. So this is a little more complicated in a general sense, because what's happening here is we have data objects that are mapped out to receive and transmit essentially objects. So these process data objects are used for cyclic communication. And one example would be, I want to know where my actuator is. What is its current position? So this type of information is helpful to understand what's going on when you have a fault, or if you needed to troubleshoot what specifically is going wrong with this node. Those are the two places I would look, whether it be using or understanding your process data objects or looking in depth into your service data objects. Okay, so the first datagram example I'm going to go into is an EtherCAT, can open over EtherCAT service data object. So what's happening here is, since we have our COE, can open over EtherCAT device, we have a few specific things that are particular to it. First thing we have what's called an object dictionary. This is noted by OD. We have various object descriptions and we have entry descriptions. So what's happening is our main device sends a request. In this request, it says, I need this specific information about this specific object in my sub device. And then based on that, it chooses its relevant command, whether that be a FPRD, configured as physical read, or FPWR, configured as physical write. So in this case right here, what we have is our datagram going in, and based on our specific device, it's a COE type communication. It's going to create an upload request, and then once that datagram has passed through, it'll iterate the working counter, and then there are various things that are handled by the main device. In this case, mailbox main, mailbox service, COE service, and any SDO related commands such as the SDO read or object read. So in this case, we have an upload response going through. So our main device has said, hey, I need to read this information from my sub device. It then iterates the working counter once it's sent that, essentially that request. And then once the sub device says, oh, I saw this information, is everything in a good state, such as our mailbox? And if it's not in a good state, what it'll do is it'll essentially abort it. It'll say, hey, when we tried to do an SDO communication, it didn't work out. This was essentially why. So in our specific example, what's happening is, if that request goes through, it says, hey, that request was good. I'm going to iterate my working counter, and then I'm going to upload my response to it. If I didn't hear back from my sub device, what's going to happen is I'm going to say, hey, I have a communication error, whether that be a watchdog timeout, whether that be an invalid request, whether that be something of that nature. It'll then tell the main device by saying, hey, that communication wasn't good, and sending it back up to the main device. So the next topic I'm going to be talking about is the process data object, or also known as PDOs. So what makes this special is, in CanOpen, you would have typically 4 transmit process data objects and 4 receive data objects. This may be manufacturer specific depending, but typically what happens is you have these multiple objects that contain various addresses of sub-devices that are mapped to them, if they are process data object mappable. What happens in EtherCAT, there's a little more to it. So instead of having 4 process data objects, you essentially have one for receive and one for transmit. And in this case right here, you also have sync managers. So these sync managers are watching process data communication. In this case, it would be sync manager 3, which you can see by the sync manager communication type. And we have our default mappings, which are stored in our COE object in our actuator as well. So basically what's happening is these objects are used to then map out inside the master or the main device. What happens here is this is handled by what's called the FMMU, Field Bus Memory Management Unit. So when you turn your actuator on and go from init to pre-op, what happens is it says, hey, I see these are your default mappings. What I'm going to do is I'm going to pass this on to my Field Bus Memory Management Unit, and I'm going to map them out to relevant objects in the main device. So this essentially makes the connection for you. A few other things worth mentioning with process data objects is in 1C32, an object on our subdevice, we can have specific parameters related to communication, such as minimum cycle time, if there's an error, or if they miss an event. So this is another good place to check if you have an issue related to sync managers. Check that subdevice's settings. Next topic I'm going to talk about is synchronization. So this is something that really makes EtherCAT a robust communication protocol. One of the things I want to point out is once you transition your system from config mode to run mode, it asks if you want to enable free run. So what this basically does is says, hey, we're going to use the local clock on your main device to track your network and synchronize your network. But there's more to it. So you have a few different options when it comes to synchronization. You have Sync Manager, which is based off of your Sync Manager's mailbox communication, specifically Sync Manager 2. And you also have your distributed clocks. And so this is based off of your sync and latch, which is configured if you use distributed clocks. And the whole idea is if you have a very large network where there may be frame jitter along the communication line, this allows you to get some level of stabilization between your various nodes in your system. The next example I'm going to talk about is the datagram example 1, which is basically how our main device requests states from our subdevice. So what happens is we have a request to set our subdevice to pre-op, and it sends a command fpwr. Then it says, okay, I want you to write pre-op state. So it then iterates the working counter as it passes this along its network. The relevant subdevice that is trying to iterate the state chain sees this and says, okay, am I in a good situation to change my state? If I am, what I'm going to do is I'm going to change my state, and I'm going to send and write to that frame. It says, hey, my current state is now pre-op, and sends that back up to the main device. And so this is essentially done inside of the application layer. So you can see where the difference happens. So our ESC is their EtherCAT subdevice controller. So what happens here is in our main device, we have specific addresses for our subdevices. And depending on their state, we say, okay, if you are in a good state, if you are in init state, and I want to move you to the pre-op state, I'm going to send this specific command with the relevant data for that state. And if there is no error, I will then change my application layer's object saying, yes, you are in this state. So this is a very, very basic example for what it is. It's a little easier to understand when you're inside of the software and you're essentially requesting these state changes. If there's anything that goes wrong, one of the first things you may see is, a communication error, whether that be a timeout, which says, hey, we tried to reach that device and it didn't work. This is configured in the watchdog settings, which basically says, how long should we wait before we time out, and other related parameters to those types of settings. So here we have a more in-depth version of the EtherCAT state machine. So one of the things I wanted to highlight is upon the init state, we only have access to our EtherCAT subdevice controller registers. So what's essentially happening is we're clearing our previous configurations, whether that be our sync managers, our field bus memory management units, and our configured addresses. Then we are going to set our physical addresses in our main device. And we are also going to start up mailbox communication. So this is essentially the first element of communication monitoring. The way I kind of say, understand mailbox communication is it's kind of like a handshake. And the whole idea is it only allows one side to essentially write the data. So when you have that mailbox communication handshake, it's very good to prevent multiple things from writing simultaneously to the same place. So that's essentially my understanding of the mailbox communication. So one of the other things I wanted to draw your attention towards is once we have successfully cleared our existing settings, we have set up our sync managers, and then we are saying, did we have distributed clocks? If we don't, we'll ignore it. If we do, we'll then set up our delays and compensations for that. And once that has all been successful, we'll then request the pre-op state, which is similar to that datagram example where it's related to the application layer. If we then request an init state, what's happening is we're clearing our mailbox settings for our sync manager 0 and 1. So if our init had successfully been set up, what will happen is we will be in the pre-op state. And inside of the pre-op state, we have mailbox communication. And so this is particularly relevant with actuators when you need to read various objects inside of the device. So essentially what's happening is once mailbox communication has been set up, we can now use our service data objects to configure our receive process data objects and our transit process data objects, as well as set up our sync managers and field bus memory management units for our device. If that all goes well, we'll then essentially start our process data in communication for our sub-devices, which allows us to be in the safe operation state. In the safe operation state, we have process data, but our outputs are still safe. And so once we go from safe op to operational, it'll then allow us to turn on our output process data. So once you've gotten to operational, essentially your system is up and running. You can now run your programs and do your configurations from there.
So this is our multi-X example. Here we have the SHA32 and the LPA20. They're both previously configured as per the previous setup example. So both of these are in the operation state. And what I'm going to walk you through is some of the multi-axis functionality. So inside of our motion block, we have axis 1 and axis 2. They have online tabs, which is similar to the NC online tab in the drive section. I've already enabled the controller and checked off feed forward and backward and set the override to 100%. Inside of the functions tab, we can set our actual position by clicking set. So now that axis 1 and axis 2 have a position of 0, we're ready to continue. Now I'm going to direct your attention towards the coupling tab. So inside this functions tab, we are going to set axis 2's master axis to axis 1, and then click couple. Now we're going to go to the functions tab for axis 1, and we're going to make an absolute position move of 360 degrees. And you can see here, even though the LPA20 and the SHA32 have different gear ratios, they both are able to move one full rotation in sync. Now we're going to go to axis 2's coupling tab and change the coupling factor to -1. This will reverse the direction. And then click change factor. Now if we go back to the functions tab for axis 1 and set our target position to 0, we can see that the LPA20 and the SHA32 move in opposite directions. We're now going to do a sinus oscillation with the frequency of 1 Hz. Since our coupling factor is set to -1, these axes are out of phase from each other. If we change our coupling factor in axis 2 back to 1, these axes will not be in phase with each other. One thing to note is if either the slave or the master axis fault out, it will effectively fault out both axes unless you decouple them from each other. So that concludes our presentation for today. I hope you guys found that helpful. With that, I'm going to pass back to our moderator so we can take some audience questions.
Now, before we begin with today's Q&A, please direct your attention to our webinar survey available next to the presentation window. If you close the survey, you can reopen the widget by clicking the icon along the bottom of your screen. Again, thanks in advance for filling out the feedback form. Your participation in the survey allows us to better serve you. And now on to the question and answer portion of our event. As a reminder to participate in Q&A, just type your question into the text box located next to the presentation window, or click the Q&A icon at the bottom of your screen. If we're not able to answer all submitted questions during today's webinar, we'll be sure to share them with our speaker, who can reply to you offline. So let's start with a question from Benjamin, who asks, what are the benefits of EtherCAT as compared to other Ethernet family products like Ethernet IP?
Yeah, so that's a great question from Benjamin. So one of the things about Ethernet IP is that it relies on T-speed or IP or UDP IP stacks. So essentially there's more latency in the system, mainly because instead of having to go and pass that frame along compared to EtherCAT, it's addressing every individual node. So the whole idea is in one single frame, you could have multiple datagrams that address many different nodes as that datagram passes through. And as that datagram is passing through, each node is essentially adding their component to it. So this is something that takes place where if you have a very large system and you're trying to address many nodes in, say, the Ethernet IP case, you're essentially having individual frames that are addressing each one of these nodes versus EtherCAT, you can essentially have a big frame that addresses multiple nodes. And if you have a very, very large system, you can also have distributed clocks. So the whole idea is you can have an offset or a delay basically baked in to say, hey, based on our propagation delay in our system, we know that there's a slight variation in that communication. So this is how we're going to address that going forward to reduce some of that jitter in the network.
Okay, thanks for that. Keep the questions coming. This one is from Charles, who wants to know, what are some guidelines for troubleshooting an integrated actuator?
Yeah, so a good place to start is a sanity check. Is it on? Do you have power? And then from there, looking at the indicator lights, a good place to check based on those indicator lights is the ETG standard to just kind of describe what state is the actuator in. If the actuator is in an unreachable state, it's good to capture the state of the network. Are other things down? And one place I like to look at in TwinCAT specifically is I like to go in and open up the network topology, which shows the layout of the network. And from there, I can see the state of each individual node. And based on that, it can give me an error. And then what I'll do with that error is I'll typically go into the backoff Infosys knowledge base and say, hey, is there some place that I can point this out with? Another good thing to look at is does our saver have an actuator specifically? Do we have a command? Are we in a mode of operation? If we're not in a mode of operation, say if our mode of operation is set to 0, we're not going to be able to move. So, that's a good place to check. A next good place to check if you've errored out is your position windows and your following windows. So these are stored in your subdevice. And so the whole idea is if you pass a certain amount of basically position window, say here, but you're actually over here, it's going to throw that flag. So being able to go in there and clear that flag is a good place to get your system back up and running and then understand, why am I getting this type of error? Do I need to look at something else in the system? Do I need to widen the window a little bit? Stuff of that nature.
Okay, keep the questions coming. Again, we'll get to as many as we can in the time we have remaining. This one comes from Lloyd, who would like to know, is buying an integrated actuator cost effective?
Yeah, so when I like to think of the cost of an integrated actuator, you're not just buying an actuator. You're buying a BLDC driver, you're buying a motor, you're buying a gearbox, and you're buying the time it takes to mate all of these together. So typically when you have a standalone motor, you'll have to match it with the driver and set your tuning parameters for that. So when you think about the cost of all these individual components and making them size effective to fit into your machine, that's where the real savings are. And also being able to simplify cabling. So when you have many cables you're routing through a machine arm or some sort of tooling, you have to think about, okay, what is the life cycle of these cables? How much stress can they take before they break? And being able to simplify that cable management allows people to create much more sleek systems without having to get into the weeds of which cable is broken. So that's one of the real benefits of having an integrated actuator, is simplifying the cabling and having that matched pair already for you. So one of the things specific to Harmonic Drive is in our strain wave gearing, we have 3 components. We have our wave generator, which is from our input. We have our flex spline, which is being driven by our input. And then we have our circular spline. And so the whole idea is these are essentially matched together. So if you can get through that process of matching that together easier and also already have a motor that is matched with that system, it really simplifies integration. Historically in the past, we've been really strong with selling component sets and gear heads. So we've wanted to take that to the next level and simplify that process. So yeah, those are some of the benefits and costs.
Great, thanks for that. Diane would like to know whether she needs a Beckhoff embedded PC to run the actuator with EtherCAT.
So in the case of Beckhoff PC, what I've done in the past is basically use an open source library called Pi Single Open EtherCAT Master. And so this has been really helpful to essentially create a pseudo master on your PC to test some of these applications. So having a Beckhoff PC can be very industrial, and it's really tailored for that EtherCAT communications. They're really great. But in terms of cost effectiveness, it may not be the best place to start if you're just looking to prove out basic functionality. So, and with that being said, essentially there's a C library called Single Open EtherCAT Master, and there's a Python variation of that. So that's one of the tools we've been using here at Harmonic Drive to kind of support these user-based applications. So starting off with PySVM, you can essentially create your own master inside, give certain simulation examples, and send commands through that to bake it into other applications if you want to leverage the power of EtherCAT.
And that's all the questions we have time for today. Thank you, Marcel. We appreciate your time and your expertise on today's topic. And thank you to our sponsor, Harmonic Drive, as well as to everyone in the audience. We appreciate your attention and participation. And within the next 24 hours, you shall receive a personalized follow-up email with a link to today's presentation on demand. Please feel free to invite your colleagues and peers who might not have been able to join us live today. On behalf of our guest, Marcel Almonte, I'm Michael Krieger. Thanks for your time and have a great day.
Thank you.